Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In my previous video, I talked about the very important notion of tensor products of vector spaces. I gave a very elementary version of the definition, which unfortunately has the deficiency that it depends on a choice of basis. In other words, it depends on coordinates. In this video, I want to give a coordinate-free definition of tensor products of vector spaces. So this is the proper definition that I'll give here. Okay, so to that end, we'll fix a ground field F here and consider two vector spaces V and W over that. Okay, and so what's the basic idea? So the basic idea is as follows. Remember, in the previous video, I introduced things called elementary tensors. Okay, now, of course, when you just think of these as vector spaces, there's no chosen basis. So instead of just looking at elementary tensors of the form a basis element tensor, a basis element, we're going to look at all of these elementary tensors as, instead. So certainly this will include all the ones that gave you the basis and the coordinate version of the tensor product of V and W. Okay, so in particular it will span, but they're not linearly independent. Okay, but that's the starting point. Okay, is we're going to look at all elementary tensors. Okay, so how do we construct these firstly? Okay, so we'll do it as following. In the following construction. Okay, so we're going to start with some vector space over F defined with a basis which is V cross W. Okay, so what does it mean? X is this vector space here. So you just look at all formal finite linear combinations of V cross W. Okay, so things which look like this. Okay, alpha 1 V1 comma W1 plus all the way up to alpha n Vn comma Wn, where all the alphas, they're just scalars inside our ground field F, and the pairs here VI, WI, they're all elements of this Cartesian product, okay? And we'll assume that they're all distinct. Okay, certainly you can just add two such formal linear combinations together to get another such formal linear combination. So you have an addition on this vector space, and you can certainly scalar multiply all these coefficients as well. So this has a scalar multiplication, and that makes this a vector space. Okay, so remember this is supposed to represent these elementary tensors. Okay, so certainly they span, but they're not linearly independent. So we're going to have to put some linear relations on these. And the way we'll do that is as follows. Okay, we're going to look at a subspace Y of this X. Okay, so this subspace is going to be spanned by certain elements. So in other words, certain linear combinations like that. And which are those? Okay, so just bear with me. I'll start go through this list. Okay, and you'll see in a moment why we want to put these linear relations on in a minute over here. Okay, so suppose you're given two vectors v prime in big V and a vector W inside big W here. We're going to look at this linear combination of these pairs, and that's going to be one of the spanning elements inside this Y. Okay, so it's V plus V prime comma W minus V comma W minus V prime comma W. Okay, then we'll do a similar thing where we have, instead of two vectors from V, we'll have two vectors from W, W prime, and a single vector from V. Okay, then you can form V comma the sum, and you want to subtract from that V comma the first one minus V comma the second one, V comma W prime. And the third type of elements you want to put in this subspace here is going to be coming from a single vector from V, a single vector little w from big W, and a scalar alpha. And any triple like this will give you two more elements. Okay, it's the following one. You look at this pair alpha V comma W, and you subtract from that alpha times this VW. Okay, so this is a linear combination of alpha V comma W and V comma W. So it is an element in this X, and we can use this to generate a subspace Y together with things of this form. Instead of multiplying the V with this alpha, you multiply now the W with this alpha, so you get V comma alpha W, and you want to subtract alpha VW like that. Okay, so this is just some subspace of this X, and I've given generators for that, so a spanning set for that subspace. Okay, now we can actually give the proper definition of the tensor product V tensor W. Okay, so it's going to be a vector space over F, and it's just a quotient space X comma Y. Okay, so it's just a set of all cosets of Y inside X. Okay, and the way we've set it up, okay, we motivate it using elementary tensors. And so where do the elementary tensors come from? So remember, inside, how do we get this? So inside X, you just have linear combinations of things of this form, V comma W. If you look at V comma W and look at its image inside this quotient, we're going to write that as V tensor W, and this V tensor W is called an elementary tensor. Okay, so things of that form are called elementary tensors. Okay, so let's just have a little look at that. So the X is not too difficult to understand. It's just a vector space with basis V cross W. But let's see what happens when you factor out by this Y. And the key point is that the factoring out by all these relations, these linear relations here, is going to give us, recover for us the important properties of this elementary tensor. Okay, so one of the things that we saw, for example, is this elementary tensor. This tensor symbol, it's like a product in the sense that it satisfies the distributive law. Okay, so V plus V prime tensor W equals V tensor W plus V prime tensor W. And I claim that this holds true using this definition just by part A here, the relations here. Okay, so why is that true? So remember, inside the quotient space, this Y is equal to 0. So all these elements here are equal to 0. So the image of this here is equal to the sum of the image of this and the image of this. So what's the image of this? The image of this is just this first elementary tensor, V plus V prime tensor W. That's the image of that. Okay, and that's equal to the sum of the images of these two. So what are the images of these two? So this is V tensor W and this is V prime tensor W. V tensor W and V prime tensor W. So here we see this left distributive law for the elementary tensor product here, okay? Similarly, all the relations inside B, what does that tell you? So here, this tells you that inside the quotient, this V tensor W plus W prime, V tensor W plus W prime, that's the sum of the elementary tensor corresponding to this plus the elementary tensor corresponding to that. So it's V tensor W from this one here plus V tensor W prime from this one here. Okay, so that gives you the right distributive law. Okay, and what were the other properties that we saw for the elementary tensor that we would like to hold? Okay, if we take the elementary tensor with a scalar multiple, so like alpha V tensor W, then you can pull that scalar out. So that's alpha tensor, the alpha times V tensor W. And similarly, if the alpha was on the W, the same thing happens. Okay, V tensor alpha W, that equals alpha times V tensor W. And those equalities just come from each of these relations here. Okay, so this here, when you set this relation equal to 0, this is inside Y, so it goes to 0 in the quotient space, which is the tensor product X tensor V tensor W. This gives you alpha V tensor W, and this gives you alpha times V tensor W. And similarly here, this is V tensor alpha W in the quotient space, and this here is alpha times V tensor W in the quotient space. So you get this equality here as well. So that recovers some important facts about the elementary tensor using this definition. So what I want to do next is give you this theorem which identifies the definition I've given here with the coordinate definition I gave in the previous video. So unfortunately I can't fully prove it on this page, but at least we can state it and we can go through half of the proof. Okay, so what are we going to do here? So how do I connect it with the definition in the previous video? Okay, so suppose we're given bases for V and W. Suppose the bases are VI for V and WJ for W. Then I claim that we actually have a basis for V tensor W using this definition, and the basis is the same one as we saw in the previous video. So that's VI tensor WJ, where I runs through all the indices that this runs through, so all the basis elements here, and these WJs run through all the possible basis elements over there. Okay, so the number of basis elements is basically the product of the bases here. Okay, so essentially the way we defined the coordinate definition of the tensor product was basically just a vector space whose basis was given by things of this form. Okay, so this essentially identifies the two definitions. But the good thing about this definition here is it's coordinate free. Okay, so let's prove this. So to show something's a basis, of course, we just have to show that it's linearly independent and also that it spans the space. Okay, so the part that's easy to show is that in fact this thing here spans. Okay, so let's just see how that works. So let's have a little think about this V tensor W. How do we get it? The V tensor W is given as a quotient of this X. And what was this X? This X was just the vector space of F with basis V cross W. Okay, so what you'll see is that this has a basis which is V cross W, so its image the image of V cross W, which is a set of elementary tensors, will span the quotient. Because in the quotient, these will always span. Okay, so we found that elementary tensors, so each elementary tensor you can write as something inside V, so that's some linear combination of these VI's. Tensor, some linear combination of the WJ's, something inside big W. Okay, so sum of B to the J, WJ. Okay, so basically everything inside this tensor product is a linear combination of things of this form. What we want to show is that actually everything is a linear combination of things of this form here. So let's see why that's true. And it's quite easy to show. So let's just see how that works. And it just uses basically these basic facts about elementary tensors. Okay, so for example, here we have the left distributive law. So we can use the left distributive law several times. Okay, we fix this vector here, and we say we've got a sum of lots of elements here, so we can break that up. So that's the sum. So this is over I, this is over J, I, J. And what you have here is that this is alpha I, V, I, tensor this sum here. Beta J, WJ. Okay? And now what can you do next? Okay, after that, well, for each of these, right, you have a fixed vector here, and you can look here, you have a sum here, so you can use the right distributive law and break this up again. So now you get alpha I, V, I, each of those, and you can break this up into a sum, so you can pull this sum out, and you have beta J, WJ. Okay? So you have the sum over ij of all these elementary tensors, alpha I, V, I, tensor beta J, WJ. And now finally we use the last part here, which tells you how the tensor product behaves with respect to scalar multiplication. Okay, these elementary tensors, how do they respect scalar multiplication? Well, you can pull the scalars out. Okay, so this is just the sum of all I and j, and you can pull the alpha I and the beta j out. And once you do that, you can see, well, now these elementary tensors, any elementary tensor now is indeed just a linear combination of these VI tensor WJ, which were the elements in the basis that we used to define the tensor product in the coordinate version of the tensor product. To prove the other half of the theorem, we need to know about the universal property for tensor products, which is an extremely important result that tells you a lot about this construction here. Okay, so to start off with, let me just remind you that the facts that I gave you about elementary tensors and how it's like a product, they actually tell you that the following map here is bilinear. The map from V cross W to V tensor W, if you send the pair V comma W to the corresponding elementary tensor V tensor W, that's actually bilinear. Okay, so that just follows from the facts above. Okay, so what is the universal property? It's encoded in this proposition, of which there are two parts. Okay, the first part is the following. Okay, let's suppose you start with a linear map out of this tensor product, V tensor W, and you have a linear phi from this V tensor W to some vector space over Fz. So you have some F linear map like that. So what you can do is, firstly, you can use this map T from V cross W, sending pairs to their corresponding elementary tensors, and then compose it with this phi. So this phi composed with phi composed with T to get you from V cross W to Z. And that's actually now a bilinear map from V cross W to Z. So it's linear both if you fix the things here and you vary inside big V, or if you fix the element of big V and you vary inside this big W. Okay, so that's the first part. Given a linear map out of this tensor product, you get a bilinear map. The other half is to show that, in fact, if you start instead with a bilinear map like this, so say beta from V cross W to Z, it comes from this procedure here, okay? So it comes from composing with this T map here, okay? So any bilinear map, beta has this form. So in other words, beta of V comma W, you can write it as coming from this phi, okay? It's phi of T of something, and T of something is just applying this to well, T of this V comma W is V tensor W. So any bilinear form, beta has the form beta of V comma W is just phi of V tensor W for some linear map phi, like this one here, okay? So another way to restate this result, and also tells you a little bit about why it's called a universal property, is the universal property tells you all about the maps, linear maps which come out of this V tensor W. How does it identify all of these? It identifies them essentially with bilinear maps from V cross W to Z. So this proposition gives you a one-to-one correspondence between bilinear maps, beta, from V cross W to Z, and linear maps from V tensor W to Z. And the correspondence between the two is just composition by this tau. Okay? So that's all there is. Okay, so let's prove the two parts. I'll concentrate on the second part because the first part is actually quite easy, okay? To check something, this is bilinear. It's just a composition. It's a composition of a bilinear map with a linear map. And in that case, you always get something that's bilinear. Okay, so let's actually go for prove the second half, okay? So we're going to start with a bilinear beta, as above, here. And what we want to do is we want to construct this phi here. Okay, so to construct this phi, we need to know, recall exactly how we define this tensor product of V tensor W. And remember, it was a quotient of x over y, where x has a basis given by pairs, okay, to V cross W, okay, things like that. And y, what was the subspace that you quotient out by? Well, there were various relations of the form A. I gave you three types, A, B, and C, and I'll just look at the ones of the form A here, okay? So the ones of this form is this linear combination of pairs, V plus V prime, comma W, minus V, comma W, minus V prime, comma W here. And remember, this relation here was the one that's going to give you the left distributive law for elementary tensors inside this big V tensor, big W here, okay? So what we'll do firstly is we're going to define a linear map from this X, this bigger ambient space, X to Z. Okay, and that's quite easy because this has a basis given by these pairs V comma W. You can just define phi tilde of V comma W to equal beta of V comma W. Okay, you're always free to do that, and you can extend linearly to get a linear map from X to Z. Okay, and now what I claim is that this actually descends to a linear map from the quotient X quotient by Y to Z. Okay, so how does that work? Well, the basic idea is the following. How can we see that that's going to descend to a linear map? Basically, we want to say that it doesn't matter which coset representative you pick inside here, the value of phi tilde on that coset representative doesn't change. Okay, so if you vary by something by Y, it doesn't change. And the way you can that we check that is we're going to show that if you apply this phi tilde to any element of Y, you get 0. So that means that varying by an element in Y doesn't change the phi tilde value. Okay, and how do we check that claim here, that phi tilde of all of Y is equal to 0? Well, Y itself is spanned by elements of this form, the ones inside that were given by the relations A, as well as the relations B and C. So let's just check now that phi tilde applied to all of these generating relations here is 0. And you'll be able to see very quickly that the same is true for the other generating relations. So let's just apply phi tilde to this here. Okay, so we have phi tilde of these three terms, phi tilde of this V plus V prime comma W, minus, so it's linear, remember? So the phi tilde of this linear combination is just a linear combination of the phi tilde values. So that's this minus phi tilde of V comma W minus phi tilde of V prime comma W. And of course, how do we define that? We define this phi tilde values as just beta. Okay, so you just replace the phi tildes with beta. So you have beta of V plus V prime comma W minus beta of V comma W minus beta of V prime comma W. And the key point is that we have to use the fact that beta is bilinear. Okay, so in particular, if you fix the W, it's going to be linear in the first variable. And in particular, it preserves addition in the first variable. So of course, this is just 0. Okay, so the fact that this is 0 means that phi tilde annihilates all these elements here, which give you defining relations for this and define Y here. Okay. Now there are similar elements B, where instead of having a sum of the V values, you have the sum of the W values. But remember, if you apply phi tilde to that, you can do the same thing here. But since beta preserves addition in the W, because it's linear in the W variable as well, you also get 0 there. And similarly, beta is bilinear, so you can pull out scalars from either of these two variables as well. And that gives you all the relations in C. So that takes care of all of them. So you will find that indeed this phi tilde is constant on coset, so you can define phi to be the value on any coset representative, okay? And that will give you a well-defined map from x cross y to z, and linearity of phi tilde gives you linearity of phi. And it's quite easy to see that by the way we constructed it, of course, okay, that since you have this relationship here, okay, phi tilde of v comma w is beta vw, and of course, what's phi of v tensor w? Remember, it's just defined to be any of these coset representatives you pick. So you can pick v comma w, so it's just phi tilde of v comma w, and that's beta vw. So phi of v tensor w, you pick a coset representative v comma w, and it's just phi tilde of that, which is that. Okay, so this linear map phi we constructed does have the correct form. So it does do exactly what we wanted to do. And that completes the proof of this proposition that these two things, they're in 1-1 correspondence, the linear maps out of v tensor w and the bilinear maps out of v cross w. Okay, and this is a very important result, and like all universal properties, it's often used to show that a certain space is big. Okay, so we showed that this was spanned by something. Okay, we gave a spanning set for it, but the thing is that if you know a spanning set, that gives you an upper bound on how big it is, but maybe there are so many relations that it's actually trivial, it's 0. Well, this is going to be used to show that it's actually quite big, and in particular prove the second half of the theorem. Okay, the second half of the theorem is that these vi tensor wj's, okay, so these vi's were a basis for v, wj is a basis for w, so we saw that this spans this v tensor w. Okay, we want to say that this is quite big in the sense that these will actually be linearly independent. Okay, so that's what this universal property will do for us. So let's see how that works. Okay, so what we need to do, we want to study this by studying linear maps coming out of it to say that it's fairly big. Okay, and to look at linear maps coming out, we need to construct a bilinear map. So let's see where we get a bilinear map from. Okay, so let's see what we want to prove. We want to show that these are linearly independent. So suppose we have a linear relation, the sum of alpha to ij. So this is just an index here. It's not powers. Alpha ij. Vi tensor wj, suppose that equals 0, and suppose these ij are all distinct. And we're required to basically show that all these coefficients are 0. Okay, so let's take a particular one, alpha to the I0, J0. We want to show that that's equal to 0. And if we can do that for arbitrary I0, J0, we're done. Okay, so let's now construct our bilinear map. And to do that, we need to do the following. Okay, so we have lots of ways of doing it, but we'll do the following. Firstly, we'll look at two linear projections, one from V to F and another from W to F. So they're just linear functionals on V and W. Okay, the first one is as follows. Okay, it's basically the dual to the I0th basis element. So it sends all VI's to 0, except it sends VI0 to 1. Okay, so in other words, it sends VI to this Kronecker delta symbol, delta II0. Okay, so all these basis elements get sent to 0 except for VI0, which gets sent to 1. And of course, since the VI's are a basis, this does define a linear map. We do something similar on this side here. Okay, we're going to send all the basis elements to 0 except for WJ0, which we send to 1. Okay, so it's a linear projection essentially onto that WJ0. Okay, and where's our bilinear map come from? Our beta here, which goes from V cross W to F now. Okay, so where does it send the pair V comma W? Okay, so what I claim is that if you send it to the product of LV of V, okay, so you apply this LV to this V to get you inside F. This is a scalar, so you can multiply by this scalar, LW of W, okay, and I claim that's a bilinear map. Okay, so let's just check quickly it's a bilinear map. So what does bilinear mean? If you fix one of the variables, say W, let's fix this W, then this is just some scalar, okay, it's inside F, that's some scalar. And then we're varying this V. Well, this is a linear map, so it's a scalar times this linear map, so of course that's still a linear map. So this is linear in V, and swapping the roles of V and W, if you hold V fixed, this is a scalar, and then you have the linear map, this scalar times LW, that's a linear map. So it is actually bilinear. Okay, great, so now we have a bilinear map. We can apply this universal property over here. Every bilinear map is going to give us a linear map phi from V tensor W to Z. So let's look at our linear map phi from V tensor W to F. And it tells you what form it has as well, okay? It's not the zero map, okay? It's something that's interesting. So the way it works, how is it related to this original beta here? It sends the elementary tensor V tensor W, phi of this linear map, phi, sends this to beta of VW. So what was our beta? Beta of VW is just this linear projection, this linear functional LV evaluated at V times LW evaluated at W. Okay, so that's what you have here. Okay, great. So now let's see how this is actually going to help us show linear independence by showing that all these coefficients are zero. Okay, so let's start with this linear relation here. Okay, and we're going to apply to this. Okay, so this is inside the tensor product of V tensor W, so we can apply this linear map V tensor W to F called phi here. So we apply phi to this. Of course, phi of 0 is still 0 here. And we can apply phi to this linear combination over here. Okay, so of course this is a linear map. So that means that you can pull out all the scalars. It preserves this linear combination. It's the sum of all the alpha to the ij times phi of this Vi tensor Wj. But what is phi of this Vi tensor Wj? Well, you just use the definition here. It's Lv of Vi times Lw of Wj. Okay, so that's what you have. Now remember, these are linear functionals, and how do we define them? Well, basically they're just projections, linear projections on, they just essentially pick out the I0th basis vector here and the J0th basis vector here. So all of these will be 0 except for Vi0. Okay, so the only I value which is non-zero is when you have I equals I0. And similarly here, this will always be 0 except when j equals j0. So the only non-zero value that occurs with j, okay, the only j which gives you a non-zero value here is when j equals j0. So that gives you only one coefficient, alpha to the I0, j0. So we've shown that this coefficient, alpha to the I0, j0, is in fact equal to 0. And this means that in particular, that in any linear relation, all the coefficients are 0. So in fact, these elements here, these elementary tensors, which are formed by basis elements, are in fact linearly independent. And that completes the proof of this theorem, and it shows us that this coordinate-free definition of tensor products agrees with the coordinate definition that I gave you in the last video. I hope you enjoyed this adventure in pure mathematics.